So carrying on to the higher level material of this May 2017 paper 2. The array sales history in the salesperson class is now replaced by objects of the linked list library class. Linked list, okay. So now we get into our linked list. Let's just take a look again at, just by way of review, what the salesperson class looks like in the sales history. All right, so we spent a lot of time with this. It's the array, now the array list of sales objects. Okay, so instead of working here with elements, we'll be getting and setting and etc. So identify the statement that will replace private sales array sales history in the salesperson class. This is where we're making the linked list. So let me see if this is ready to go. I guess so it is. So it's going to be linked list, yeah, linked list of type sales, and it will be called sales history is assigned new linked list of type sales, open close parentheses for the constructor of it. That's it. And there, well, there it was. Public, private linked list sales history. Well, that's interesting. Now this is the first time I've come across a different answer. Yeah, actually, so I think either would be fine, frankly. But if you're just going to define it, then you could define it. But sooner or later, you've got to do the rest of it, right? Sooner or later, you do have to do that part of it. So I'm actually going to say that I don't like that as an answer. I think this is better. Okay. B, construct the method largest sale. So we actually do end up making this largest sale. Right, I remember this one. Largest sale was just sitting there. I don't know if we used it or not yet. We used calc total sales. I'm not sure that we used this, but it calculates the sale with the largest value. Okay, so already I can imagine we're going to be looping through. Is there anything else here? 5 marks. All right, so looping through the array list and getting the largest. Well, each sale, let's just remind ourselves how the sale works. The total value of a sale isn't just its value. Remember this, it's its value times the quantity. So we're going to have this list of sales, and we're just going to keep track of which is the largest double when these two of each of them are multiplied together. And interestingly, compared to the other paper 2 that I did, they didn't give us any, they didn't remind us of any of the linked list functions. And I don't have them up here right now. Let me just do a really quick search. I mean, you won't be able to do this on an exam, obviously. You've got to have these ready, but I just want the list up in front of you. So let's go linked list. Let's just go linked list and take a look at the list of functions. Is this going to do it? Not really. I mean, there are a bunch that are there. This won't take long. I mean, I know what they are, and you hopefully know what they are too, but they're these, right? But where are they listed? There we go. That's what I was looking for. So we've got things like add and get and remove, right? And sometimes they do give you those on the paper itself, but they're not here. We should be all right. Okay, because you should have those in your mind ready to go. So here I go. All right, I can now get rid of that. Okay, so this is first of all the whole thing. So we're going to have public whatever whatever, and what's it returning? That returns the sales object. Okay, or it could be private, but public. Oh, you know what? That's right there. So we don't want to look at that. Right, it's returning a sale. It's called sales. Public sale, largest sale. And does it take in anything? No. So that's good. And at the end, again, I always like to do this. Return. Well, I'll just do blah, blah, blah for now. Okay. And I know I'm going to be returning a sale. And I'm going to loop through my array list. So same old, same old. And this is sales history. It's dot size, not length. And we will be going through the whole thing, right? Now, it's one of these things where we're looking for the largest. So I think the last time we did something like this in this paper, I remember to do it before I did the for loop, but here I forgot. So let's do double largest starts at 0. Right, and anytime we find one of these sales histories that has a value which is larger than the largest, it becomes the largest. So, and I guess we also have to keep track of where that is. So we'll do int largest index. Starts at 0. And I know that I'm going to have to multiply together one more time the value and the quantity, and that's going to make for a long line, particularly with this big font. And it's just an alternative way to do it. So I'm going to, rather than do the great big long line, I'm going to do a couple local variables. You'll see what I mean completely as soon as I start it here. I'm going to go that the value, so double value is going to be sales history dot get, not chunk dot get I dot, this is still going to be a long line, isn't it? So is it get value? I've got it right here. So get value times, what I'll do is just for the video here, I'm going to just make this smaller, this line smaller, to get it on one line. I think I'd rather do that way. Okay, times sales history dot get I dot get close, get, well, maybe value, no, so 12 for font size. Right? So looping through this sales history array list, and at each step along the way getting a value, which will be, that wasn't a very good name for it, let's call it total. I'll call it total. The value times, that's wrong, quantity. You probably saw that. I didn't. Right, value times quantity for each one of them gives a total. And then if total is greater than the largest so far, first time through it would be 0, then largest is equal to total. Easiest way to do it. And then we can keep track of where the largest index is. Is going to be the I. So this is an involved question. It's a good one. It's a fair one, I think. And you'll get one of these largest or smallest or average or whatever. You'll get a question like that, and you'll get one that's in all likelihood going to loop you through an array list or an array. So there it is. We've gone through and we now have an index of the largest, and we want to return, and I left that over here. Now what am I returning? A sale. So I've got to be careful that I'm not returning largest. I'm not returning largest index. I'm returning a sale. So sales history dot get I, or dot get largest index. Sales history dot get largest index. That returns the sale at this index, which will be the largest. Don't think there's anything missing with that. We'll take a look at the marking scheme, or the answer key. This is 15D, B. Okay, so here I definitely did that great big long line, which is harder to see. Okay. Well, okay, I did a couple of different things, but only a couple. I mean, -1 instead of 0, whatever. But in terms of, that's the one thing I did differently here, right? In terms of returning the sales, so I just kept track of a sales through it. I said if blah, 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 then the max sale is S. So then I just directly returned the max sale, where here I kept track of the index, right? And I used the index and get in the return statement to return the sale. So you can pause on that if you want to think about that a little bit, why both of those work. But they're both returning a sale. Right, it's just that's hard to follow here. Whereas S, what's S? Looks like I might have been tired when I did this, made another little error here. If sales history get the value times it is greater than largest. Largest is get value. Okay, I think that's just, that would have to be sales history get I, is what that would have to be. So that's wrong as well. I can change this here. Sales max sale would be sales history dot get I. Where the S came from, I don't know. Okay, so that's the alternative way to do it. Sorry about noticing that mistake. Next, or I guess not sorry, but noticing the mistake. Sorry about the mistake. 16, following node class defines a node to be used in a binary search tree. So now we're in binary search trees. Okay, right, the node left, node right. Those are the attributes. And this is to make a new node, and you start with a null and a null and the data. Okay, and you're probably more familiar with and ready to recognize a node for a list, which just has a node next. But we did look at this that you wouldn't want to be calling this class node. You want to be calling it binary tree node. But yeah, you would. So anyway, A, using the above class as an example, describe the use of references as a data type. Okay, that's a little bit of a different approach to both trees. It's like combining trees and reference data types, but fair enough. A reference data type, I mean, Pimped Up Pizza, right? From way back when, that was a reference data type. The data itself is an address. So you probably want to say something about the fact that this is not just a reference type, it's a self-referential data type if you're using the above example. So here's your canned answer. The canned answer, this would take some stuff. This is an original question which requires some thought, piecing together some good stuff that you know. That describe the use of reference as a data type. Well, normally data types are primitives, which are simply the data itself, like an integer is, or init is an integer. String is words and letters. But reference data types are addresses. So a node instance would actually be, literally be, an address. And in the case of this example, you'd probably go on to say for your 3 marks, it's a self-referential data type in that not only does it have as its attributes reference types, but they are the reference type of the type itself. Take a look at the answer key. And now I'm going to be looking at this with a little bit more critical eye. So I'm going to read through this in case I was getting tired when I was doing this. Okay, I said that exactly pretty much. Yeah, okay. Okay, that's fine. So you can read through that, pause this if you like. And then we have a tree. The following binary search tree has been created using the data items. The nodes have been labeled for easier identification. Remember, how these are built. They're built in a balanced way. So 33 goes in first, 12 is going to be to the left, 14 goes in, it's less than 33, greater than 12, goes to the right, 50 is greater than 33, goes here. So it's a pretty small binary search tree, but it is a binary search tree. The method print has been called with a statement, print root, and root's that, binary search tree. Public void print, node. Okay, if node equals null, return, you're finished. Then print, there it is. Is this the first recursion? I think so, in this exam. So here's your recursive question. There it is. And we haven't done this, right? Let's be clear. Hopefully in April we're going to do it, but I will explain this as part of this video right now. And we've done a little bit, and maybe you'll get this, but if not, just let it wash over you for now, and you can come back to it later on. So there it is. We're calling root. We're sending root. And there's the root. And is it null? No. So we're going to be printing the left. So we go in here and we call print again. So you're right back up into another instance of this. And we say, is this null? The answer is no. So what we do is we call print of its left, which is right here. So then for this, which is just null, we do all this again. And we say, if it's null, return. So it is. And we kind of cancel that out and come back to where we left off here. So that's the sort of thing that I'll be talking about when we do whatever they're asking us to do in all likelihood. So there are just 2 questions left. So using the data in the given binary search tree, trace it. We're going to trace it. We're going to just give the output. But more than that, trace the method print, showing clearly, that's the tough part, the recursive calls, the node that is being addressed, and the order in which the data is output. It's almost like this part of it, which is maybe 2 of the 5 marks, is easier than doing a trace table or something that helps us see how this is traced. So I'm going to do what I did in the marking scheme, right, which I saw before, and I think this is clear. Is it a trace table? No, but we should be able to get by, and I think it's a better way to do it anyway. So I've got Photoshop in memory, and I guess I've got to take a little bit of time. Whether I fast forward this or not, probably I won't, because this isn't that long of a video. So 33. now. So I won't fast forward this. I'll just do it live. All right, there's our tree. And that's about as good as I'm going to be able to do for arrows. Again, it's a simple binary tree, but it's a binary tree, and it has a root. So we want to trace it. Oh, and we're going to need to have this. How will I do this? I need to have this in front of me over in Photoshop. Okay, here we go. A little bit bigger, maybe. Recursion, recursion, recursion. Here we go. Maybe I can do blue for my trace. And if you have a couple of different pencils, pens in the exam, that would be a good choice. So this is the root. We go in, and I'll do my output over here maybe. Output. We started the root. And we go one line at a time. Public void print. No, okay. Root is sent. Root is sent. So node is root is this 33. If node is equal to null, well, it's not. Do we return? No. That's just one line. So we move on and we go to print, which is the name of this function, node.left. So this dot left, now we're to here. So the first stage, like I do in the answer key, the first thing that we do is we go down to and call 12, right? When we get to this point, I know this is new to you, when we get to and it's difficult, when we get to this point, we call another instance of print. This whole thing is going to be print for not node 33, but node 12. Okay, so now we're here. And we go in, if node equals null. No, we don't return. Print, which is this method again, node left. So we go to the left, which is null. Okay, and we do all this again. Null gets sent in. If node equals null, it does. So this step is equal to null, so we simply return. Back to 12 where we left off. It was on a stack. When we put it on the stack, we had just called this. So that is now done. And we move to the next line, which is print, another instance of this, node right. Node right gets sent in. If node equals null, no it doesn't, because this is the right and it's not equal to null. So we go down to the next line. And I better draw this. So this is like fourth step, we go down to here and we ask and we look at this one, it'd be like 5. Right, so now we're to this null. And we say, is it equal to null? Yes. So we return. Okay, we return to here where we put it on the stack. We put this on the stack when we had called the left. So we still have these 2 lines to do, right, for this one. So we go to the right of this. How am I doing this? 7. And to the right, there's null. So another one of these. Is it equal to null? Yes, we return. the 8th step. And so we're back to this. This is the tricky part. We're back to this. Where are we? At this line, this line, this line, or this line? Well, we checked that back a few steps ago. We checked that with 5 and 6. We checked that with 7 and 8. And so finally, with number 14, it's the first one where we've actually drilled down in the recursive method to the final line, which is to print line. Node data plus a space. And it's print line, so 14. So 14 plus a space is printed. Okay, and so now that is finished. And I mean, these nulls are finished too. I could have done that. You know, I could even wrote null, but I didn't. So they're all finished. Now this is finished because we got down to here. Pop. Okay. So when this gets popped off, when this print of 14 gets popped off, where were we? Well, we were looking at the right-hand one from 12. We were doing this with 12. And so having checked to see was null, no. Check to the left, which was this business. Check to the right, which was all this business. Now we get down here for 12, we print out the node.data. And probably some of you are saying now, oh, okay, now I get it. So now we're up to this line and the number 12. And there was a space there, so print line, not print. So why would you even do a space? How do you undo multiple times? You'd think I'd know that at the eraser. I don't know if you lose any points for this, but it is, each one's print line. So yeah, get down to here and we print the 12. Okay, which means we've done all the lines for the instance of print for 12. Which means we go back to, I guess this would be like 9. This would be like back here to 10. That's why these traces, when you do them in a table, they're pretty big. So we're back here where it was this original call, this very, very original call. All we did is we checked that, no, and we did the left. Right? That's all the left of 33, but it's now finished. So we move to the next line, which is another print, this time for its right. So we go down here. And we've sent 50 in, 50 equal to null, no. We look at its left. This is left null, it is, so that's just out of memory immediately. Whoa. And so now we're back to the print for 50. We've done the no, we do the right. And is it null? It is, so we come back. Okay, so now with the 50 instance of print, done that, check to the left, check to the right, it's out, we come back and we print. This is for 50. Now we're finished with 50, node 50. And we come back. I may have missed an arrow here, I don't know, but I'm at an even, so that makes sense. And now we're back to that original call way down at the bottom of the stack that got interrupted way back in the beginning. And we had done that as the very first step. We had looked all the way left. Now we looked to the right, and we're finished that. And so now we print out node.data, which is 33. And I'm going to compare that just really quickly, just for my own sense of pride, I guess. 18, 19. Well, no, my numbers are mixed up here. I guess what I did is I included like a line for 9 and 11 and 19 and 18. So, but my numbering I did slightly different. I just did numbering for the arrows here, and I did numbering for being at the node itself here. But in terms of the directions and the way that it works and the output in terms of the answer, it is the same. So April. I don't know when, but sometime in April. C, we'll go through some more recursion in earnest. C, well, we didn't read this yet. The method smallest returns the smallest value in any binary search tree. The method will be called by the statement int s. Okay, so we're going to be making a method, I guess. So it's going to be a method that takes in a node and it returns an int. So by making use of the same node class as shown previously, construct the method, so it is construct the method's smallest. Note, you can assume that the data in each node is an integer and that the tree is not empty. Again, things like that are just so you don't have to add extra if not empty or if, like a try catch for an integer or a number formatting error. So you don't have to worry about that sort of stuff. So 5 marks, tough question to get out of the blue. When you look at the answer that I'll give you, you're like, okay, I get it, but would you get it on a test? Well, it's the hardest question of the hardest. One of the hardest exams in IB, right? Higher level, paper 2, computer science. So let's think about this. I bet you if this tree was a bigger tree with a bunch more nodes, it would be more obvious what you got to do. And I almost feel like I just want to do it because here's the thing. The way the binary search trees are organized is in a binary greater than less than way, right? So the smallest is always way over here, right? The smallest is always the furthest to the left. And sometimes it has a node to the right, but it will be bigger than itself, right? So all we have to do, quote unquote, all we have to do is drill all the way down to the left, and then we found it. In this case, while while I suppose node.getLeft is not equal to null, keep on moving, keep on moving, keep on moving, keep on moving. Sooner or later, you're going to get to the smallest. So how would that look? And that's the answer, right? How would that look? Doing it over here, we don't want to see it, we're not. So at the very least, with something like this, you can certainly get your header correct. So public int smallest, and I guess it's going to be within the same class, so just like that. So what's it going to look like? While, because we don't know how far to the left we're going to go, while, I guess it's going to take the root. It's going to take like node n. While n.getLeft, and one of the reasons why they would have said you can use this, okay, it doesn't show a get left, but there would be a get left. It doesn't show even private here, but there'd be a get left. So while this is not equal to null, why don't we use the term current? So let's go node current for traversing, and you will have looked at all sorts of stuff with current and all sorts of really complex things. Hopefully before you have any question like this and you're like, oh yeah, let's use a current to go through it, is going to be the root or n. So that's where we start, and then the current just keeps on getting next. Current becomes current dot get next, which will look familiar when you get this back into your working memory. And that's actually it for 5 marks, believe it or not, unless I'm missing something. Because, again, then you're going to be at the end. And again, it would be a lot more clear to see, I think, if this was bigger. And you're returning the int. That's a nice little fine point. So return the current. Is that going to do it? Yeah. Current dot get data. Yeah, because data is an int, so get data. If I can finish this off, dun, 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 there it is, done. Okay. Right, so just as I end here, same old idea of on paper 2, tough. And I'm not going to repeat again the statistics. You're just looking for the stuff you can do and making a good effort at all of it. And yeah, getting all you can from this really challenging but really quite interesting when you see what you're doing, certainly applicable in your future paper. So that's it for paper 2, higher level, May 2017. False alarm, I should have taken a look at the answer, and yeah, it's get left, not get next, because this isn't a list, this is a tree, so it's get left, get left, get left, get left. My bad. There, that is that.